Hi, this is Nathan Tintle. In this Learning Goal video, we're going to talk about how to conduct a theory-based test of a single mean, also known as a one-sample t-test. We will use the estimating elapsed time dataset to talk about this learning goal. As you know, theory-based tests don't use simulation to obtain a null distribution. Instead, they use mathematical formulas to predict what would happen if you simulated. When we conducted a simulation on the estimating elapsed time dataset, we saw that the simulated null distribution took a familiar shape. It was a bell-shaped curve centered at 10, the null value. When certain validity conditions are met, we're going to be able to predict that distribution, a nice bell-shaped curve, very similar to the way we've done before for a single proportion. Now, as it turns out, mathematical theory doesn't do a good job of predicting the distribution of sample means. They actually do a good job of predicting the distribution of the standardized statistic. Now, we've seen standardized statistics before. You take the sample statistic, in this case the sample mean, you subtract the null hypothesized value, in this case the hypothesized population mean, and you divide by the standard deviation of the statistic, in this case the standard deviation of sample means. Now, a version of the central limit theorem, which we've talked about before, says that the standard deviation of sample means can be estimated by s over the square root of n. What this means then is that your standardized statistic, in this case called a t-statistic, we'll talk more about that notation in a minute, is the sample mean, x bar, minus the null hypothesized value of the mean, mu 0, divided by s over the square root of n. Breaking this down, the observed average estimated elapsed time is 13.71 seconds. That's x bar. We subtract 10, the null hypothesized value of the mean, and we divide by 6.5 over the square root of 48, which is the sample standard deviation, 6.5, divided by the square root of the sample size, 48. Ultimately, this gives us a value of 3.95 for this thing called a t-statistic. The way we can think about a t-statistic is essentially just like a standardized z-statistic that we've seen before. We'll talk more about that at the end of this video. So we can predict the shape of these t-statistics very well, and that's what you see in this graph here. The predicted shape of the t-statistics will take something called a t-distribution as long as certain validity conditions are met. In this case, as long as your quantitative variable has a symmetric distribution, or if you've got more than 20 observations and your data is not too strongly skewed, you'll be fine. In this case, the sample size is 48, and while there is some skewness in the estimated elapsed times, it's not strongly skewed, so our validity conditions are met. Because the validity conditions are met, you'll see that the theory-based p-value of 0.0003 is very close to the p-value we got from simulation, 0.002. A few words of caution. Why are we talking about t-statistics now instead of z-statistics? Well, practically that actually doesn't make much of a difference. The way you interpret t-statistics, in this case 3.95, is almost identical to the way you interpret a z-statistic. Hey, a z-statistic of 3.95 would be big. We'd see that's strong evidence against the null hypothesis. Same idea here. S is an additional parameter we have to estimate from the data. This additional parameter means that there's actually more variation in the null distribution. There's less things that we know. So a t-distribution looks like a bell-shaped curve, except it has what we call heavier tails, meaning there's a little bit more variation than in a normal distribution, a z-distribution. But for all intents and purposes, they're not much different. And as it turns out, as the sample size increases, t looks a lot like z anyway. So the way practically that we interpret t-statistics is pretty much just like z-statistics. Remember, because this is a theory-based approach, you need to check your validity conditions before using. And remember also that p-values from simulation or theory will be similar as long as the validity conditions are met.